So when we were initially talking with Justin about giving a presentation, he was going to talk about some simulation work that he's performed of the sun's interior. And then it turned out that he got some advice that, some of the stuff you're doing here, it is, really special. You need to hold it a little bit close. And so what we've done is we've swapped the topic right here for Orion Nebula, Wonders and Mysteries. And like I said before, today I went through the presentation, I reviewed all the slides, and about 90% of the content there was a learning for me. So I hope that you really enjoy what Justin McCollum is going to be talking about. A little bit of background right here, BS in Physics, Portland State, MS in Physics. I do not know what PGP is.
That's MS Physics at Portland State University.
Okay, what about this one right here?
That's a postgraduate program in artificial intelligence and machine learning.
All right, okay.
Yeah, it's MS Physics.
Yep.
Portland State.
And Justin is a real omnibus fellow with respect to what he can do professionally. He does work at Space Center Houston, University of Houston Clear Lake, American Data Science. A wonderful fellow with respect to STEM outreach. He's done a lot of work at Texas State Star Party. In fact, one of the things that you'll see when we get to Joe Califf's presentation later today is there's a slide in there that has a picture of some of the participants. And whose photo do you think is there but Justin? All right, okay. And then, like the last bullet says, he's also been very active in research and also course development at Clear Lake, and until recently, he also worked at Lamar University. I'm going to be quiet, so Justin, why don't you come on up and talk to us about the wonders of the Orion Nebula.
Try to keep this within a reasonable time. Okay, let me see if I can get this connected. Okay, everybody hear me? All right. Down arrow gets me to where I need to go. All right. This is probably one of the more famous objects that we find in the night sky in the wintertime. It's been known really since, well, literally since the 17th century. There are actually Arab scholars who have documented seeing this fuzzy structure as sort of this interesting sort of unfocusable star in the night sky long before Charles Messier. It's only when we have Charles Messier that we get to see that this is something that is other than being just a comet. So one thing we can know about the Orion Nebula, we have some facts. One, of course, it's located in the constellation of Orion. Two, at least looking at the stars inside this bubble of gas, the trapezium, you can measure the distance roughly to around 1,344 light years, give or take about a couple hundred light years. It's one of the most active stellar nurseries in the Milky Way galaxy. That's from radio astronomy scanning the whole of the Milky Way. This is probably one of the top 3 star-forming regions. It has very intense areas of star formations and indications of thousands of planetary systems undergoing various stages of development. It spans at least the visible part that we see. Not all of this stuff, but just this area right here ranges between 24 to 40 light years in terms of what you define as sort of the boundary of the Orion Nebula. It's mostly just hydrogen gas. I mean, it was first observed in the Western world by this astronomer Nicolas Claude Frabet de Parisac in 1610. He was one of the first astronomers after Galileo to be using telescopes to study fuzzy stars in the sky. What we know is that there's enough material here for it to last another 3 to 5 million years. So this is not something that just exists like a planetary nebula where it's around for a few thousand years and then it just disappears. What we know is about 2,000 times the mass of the sun. So we have enough material here to form thousands of stars, mostly just red dwarf stars. What we can be certain about the volume is that based on 24 light years, it's a volume of about 10,500 cubic light years. And these stellar nurseries are going to be covering tens of thousands of light years. You've got a lot of this radiation that's blowing apart the the dust, turning it into gas. So we have a lot of gap between the stars that are forming inside what we call these Stromgren spheres, these bubbles of photoionized radiation, where basically the stars emit so much intense light that they literally turn the dust to gas. The gas glows from ultraviolet effects that release visible light, but it produces a shock wave that pushes the dust out to come in contact with the interstellar winds. We can be certain that, at least on the average density, it's about 600 atoms per cubic centimeter. And when you realize our Earth's atmosphere has hundreds of trillions of atoms per cubic centimeter, you can fly through this and miss a lot of the gas. So this is Theta 1 Orionis, the trapezium. You've got 4 monstrous stars. You have to realize that this is a very dense open pack cluster. There are literally some 6,000 stars in various states of formation that are in this cluster because of the proper motion, how the stars are moving, the spectra of the stars, and in the age range. But really the massive ones are these 4 OB class stars. This is the Eridanus loop. This is the Barnard's loop. This is the Lambda Orionis ring, which is Barnard's head. All of this, with the exception of this, is part of the big Orion Eridanus giant molecular cloud complex that stretches for thousands of light years. The Eridanus superbubble is a shell of gas. It's 1,000,000 Kelvin in temperature. When you get a lot of stellar remnants in here, particularly a combination of the OB stars, the big giant blue stars, and a lot of neutron stars, it's going to be at temperatures of hundreds of thousands of kelvins in temperature, and that's going to emit immense amounts of radiation that literally heats up the gas. Most of this is invisible except in the X-rays because of the high temperature. Most of this is going to be from the OB stars. We're talking about 80 to 100 suns. Oh, gosh. This is going to be several degrees of sky because this represents the 3 stars here represent the head of Orion. So it's something that is about probably 5 or 6 full moons across. No, the belt of Orion is not even in this area there. I mean, you have to realize this is a scale that covers many square degrees of sky. The winds themselves, we have to remember that the energy in these winds from these massive stars, of which they're so rare, it's like 1 star for every several billion. The scale's around 10 to the 44th joules. So think of the solar winds emitting every second enough energy to be the equivalent to the 10 billion year lifespan of the sun. There's just a lot of energy being generated. And all this is released from the more massive of these O-class stars in the 100 sun mass class within just a few seconds. So every few seconds you get 10 to the 44th joules. Another few seconds you get 10 to the 44th joules. So lots and lots of energy. And there's just enough of this to where it gains enough escape velocity that it can actually leave the gravity well of the Milky Way galaxy and escape out into intergalactic space. Because a lot of the gas is moving, in some cases like 10 or 15% the speed of light. Now, there are other facts about the superbubble. This is 1,200 light years of space, 500 light years spread between our local bubble, because we are in a bubble in our solar system, where we have a lot of gas and dust. It's a bit denser than out of the interstellar space. There are lots of dark nebulas in here. There are multiple stellar nurseries. We've got Orion's Nebula. We've got the Horsehead. We have up here the Witchhead Nebula. There's also several other nebulas, the Flame Nebula. The Witchhead Nebula is right over here. We have lots of reflection nebulas, lots of open star clusters, hundreds of them. So here's the Witchhead Nebula. It's being lit up by Rigel. It's a reflective nebula. It's actually an inner shock wave from the over part of Barnard's loop. So you can see it. It's not there. I'm sorry. It's right here because Rigel's right there. So that is right there. That's trying to look at all of this at high focusing and high resolution and high exposure times, just revealing all the dust here in radio waves. The chemistry is very exotic. there are chemical elements in the Orion Nebula that are equivalent to what you find in a refinery for making like synthetic rubber. I mean, you've got formaldehyde, you've got methylformate, you've got acrylonitrile, which is one of the chemicals for synthetic rubber. You've got methyl ketones, you've got molecular oxygen. There is just as many exotic compounds you find in the Orion Nebula as you would find, let's say, on the moon of Titan. There are a lot of starbursts that we find from vast surveys from the Hubble Space Telescope. So this is an area of intense research looking at stellar evolution, the formation of stars, planetary developments in the area of astronomers focusing on protoplanetary disks, you know, how planetary systems are forming, how they're going to create planets that are susceptible to life, the concentration of organic chemicals. So there's just a high concentration of protoplanetary disks. The best concentration is known for the methyl ketones, which are basically like methane molecule stripped of a hydrogen atom, because you can correlate that with the presence of water. And there's a lot of what we call photorecombination, where you can take these methyl ketones with carbon dioxide and produce a lot of complex organic molecules, a lot of polyatomic organic ions, because of the tremendous amounts of ultraviolet radiation literally playing sort of Jim Rummy with a lot of these organic molecules. They're literally moving around atoms. This is very interesting. This is the Orion arm right here. I don't know if anybody's ever seen this in a telescope. This boundary right here, because there's the trapezium. That's the Orion bar, as we call it. The Orion bar is very special because one thing is that we've got interesting features here. This is a red dwarf star forming in real time inside the Orion bar itself. The material is literally falling into the star like a drain because it's so compacted because of the radiation that will dissipate the dust, turning into a gas, but also squeezes it in because the radiation pressure is squeezing in the very dense material. And then the gravity of the red star is the gravity of the red dwarf star is literally having it fall inwards to form it. The intense UV radiation in the trapezium will only last for a few million years, which is nothing compared to the lifespan of the Earth. So a lot of things are forming here in quick time. Much is unknown about how the methyl ketones are forming inside the Orion Nebula and leading to the complex molecules that are forming inside of it. In fact, one of the big things about the James Webb Space Telescope is, yes, we want to see the mysteries of the universe, but even close by, where we only need ultraviolet and visible light astronomy, the infrared astronomy is able to penetrate deep to look in the interior and reveal the secrets of stellar formation regions that you don't get with ultraviolet and visible light because of the blockage of the dust to those particular wavelengths of light. So this is the complex chemistry. The primary driver is photochemistry. So you get a lot of photons that mess around with the electrons, combining hydrogen and carbon, and they just end up with this complex chemistry. You have what we call a lot of endoergic reactions, where basically stellar energy is absorbed. You absorb the starlight, the star energy, and that just adds energy to really stimulate chemical reactions when combining basically forms of methane and carbon and oxygen to create the complex molecules. And we end up with a lot of methane and hydrogen ions that act as these charged atoms, these ions, that are literally getting a lot of their energy because the gas is being irradiated by the far ultraviolet radiation coming from the intense stars. Okay, so some recent supernovae in giant cavities. There's a program that was developed that shows that 3D reevaluations of Barnard's Loop, because the environment right inside here can affect all the nebulous material in here, including the Orion Nebula. One thing is, this is data from the Gaia spacecraft, so you get huge cavities of dust and gas that are literally forming, probably from supernova explosions, multiple supernova explosions over the last 3 million years. So one thing about this Orion spur is that there's an unusual degree of stellar activity that we don't find in many parts of the galaxy.
The Orion, yeah, if you can point out where on that picture the Orion Nebula itself is.
Scale.
Yeah, that they're not to scale.
They are too scary.
They are. Okay, so point out where the Orion Nebula is.
Well,
so
there's the
people,
Orion
yeah,
Nebula.
yeah. So people, I want them to understand where the Orion Nebula is in
And this
that
is
picture.
the dust ring.
Okay,
And this is the inner boundary
all right.
of that dust ring down around here.
Very cool. Okay.
So, I mean, it's just, I mean, you're talking hundreds of light years
Yep.
across space.
Okay.
Oops. Let me go back.
Okay.
Now, one thing
Thanks.
is that these are cavities of dust and gas. The radiation literally has its own momentum because it's able to add it to the dust, stimulates it as a gas, and it literally pushes out. I mean, here you've got the dust up here in the yellow. You've got the supernova tracer, which is the nature of the radiations that moves along the gas itself. That gas gets transferred its energy into the galactic winds around the surrounding material that's been gathered from previous giant molecular clouds, clouds of frozen hydrogen and carbon monoxide that get stimulated into this bluer, intense radiation. But one thing about this is that we're seeing how open star clusters are moving at very high speed in this region with respect to other open star clusters that we see in the Milky Way galaxy. So as much as gravity is an influence, intense electromagnetic radiation on this scale can really move a lot of material over vast distances. So this shows here the various different features. There's a lot of Wolf-Rayet stars around here. These are giant blue, supergiant luminous stars that literally blow out their hydrogen layer. So the inner part of the star is exposed. It's just a lot of intense helium, and that intense helium emits radiation in the millions of degrees Celsius. And that radiation is going to be moving around the clusters of stars. It's displacing a lot of the dust, and that can affect how the Orion Nebula is going to be surviving. So the fate of the Orion Nebula is being dictated by the radiation that's literally eating it from the outside inwards by all this intense activity. Okay, so interpreting the environment, the blue star, which is in the center there, is the flux center of the Orion Nebula. The orange star, which is, there's the flux where the radiation is pouring from, but the original orange star that I showed in that image is part of what we call the OPPB1. It's a subgroup of what we call a big stellar association. There are a huge concentration of the O and B class stars that make up multiple star clusters that are separated in different groups. And so what you get is that the stars themselves are in the environment where they are still carrying on the radiation to form that big, huge bubble, but they're being pushed around by both gravity from other clusters of stars, because as much as gravity is an attractor, it can be like a slingshot, and then there's just the intense force of radiation in this environment. It's actually made up of two subgroups that are made up of multiple star clusters. There's the Brisenia 1, which is a kinematic open star cluster. It's sort of to the northeast of, actually to the northwest of Orion's belt. It covers 1 degree of sky. It's very visible to binoculars, but you get a lot of radio expansion. It's very coherent, which means it's very consistent as it blows material out from a common center. There's a lot of stellar feedback, so there's a lot of continuous inflow of radiation, and there's a lot of the effects of the starlight, the intense radiation from the stars that are actually driving the forces within this environment. And then that radiation creates a very it surrounds the influential interstellar medium, which can then work its way around that dust cloud and just concentrates it into a nice large shell. So this actually is a 3D program, so you can see where we have the areas of the stars, the shells blowing out. Here are the 3 belts of Orion right there, so you can see where we have the stars with Rigel and with Betelgeuse. And when you look at this 3-dimensionally, this is over hundreds of light years of space. And one of the things this is being used as a tool for is to see what's going to be the progression of the flow of that dust by the radiation being blown out by these groups of stars as they infect the environment for the formation. So here's the expansion of the gas, and that expansion is due to the outflow of the radiation, not from one star, not from a single cluster of stars, but from stellar associations within a stellar association. So right here, we get where we can see the various groups of stars. This is Persenia 1. This is the OPB near group. So this is in the area not far from Orion's, well, you've got the belt of Orion, then you've got the upper part of Orion. And so it's all those intense stars in the upper part of Orion going up to Betelgeuse. Okay, and then what's interesting is that we can look at what we call the Hubble flow, the outwards of the speed of these stars as they increase in speed, as they are moving faster and faster and further because the cumulative effects of the radiation as it's actually blowing the stars outwards. So over time, these groups of stars are going to spread apart from each other. More so, it's more in effect by the radiation versus that of the gravitational force of all these combined stars. Gravity is going to keep a lot of these open star clusters together, but there's a threshold where the radiation is a bit more intense. It can move apart the stars themselves. Not blow up the stars, but separate out the stars. So there's a huge battle between the intense fields of gravity and the tumultuous amounts of radiation in this environment. Okay, and one of the things is mapping out aluminum-26. That's basically an isotope of aluminum that we find in the dust. It tells a lot about the process of star formation, the concentrations of stars, and where is the dust moving, and how that affects the flow of radiation and the concentration of mass to deal with the concentration of gravity. So what's interesting, it also deals with the ages of the stars. The reality is that this is probably the more likely scenario here, where you look at how the stars, the age of the stars, the productions, and how much they're being generated by supernovas. It's very likely that half of the stars were generated by one or two supernovas that literally became their own stellar nurseries. The older stars are in an age range of slightly over 9 million years. The younger stars are about 7.5 million years, less than 7.5 million years old. And what this tells us is that none of the stars are going to be older than 1.4 million years, but well, not younger than 1.4 million years, but not older than 8.25 million years. And here we can look at the chances of there being the supernova explosions. And what we find here is that we find where there's a 40% chance where there was a supernova that went off in the last 10 million years, and only a 10% chance of 5 or 7 million years ago. So it allows them to concentrate where are likely the cases where the supernovas occurred. And so we get where we see how the star formations are producing. They create generations of supernova. The radiation is blowing outwards. It's moving the stars all about. So we get tremendous movement of both the dust and the gas and the velocities. And we look at the evidence. One is just looking at the characteristics of the stars by age. One is the motion of the stars. And there's no evidence for this large-scale expansion that has been found other than looking at the movement of the stars. But then there's the spectra. One thing about Barnard's loop, it's best studied when combining hydrogen alpha with aluminum-26, because that tends to be a marker in which you can look at the behavior of the dust. Okay, so this is the mighty trapezium. We don't know much about the mass. The top 5 stars, the A through E star, between 15 to 30 times the mass of the sun. They're very close together, so the radius is like 10 light years. But we have to remember that these are literally dictating the radiation and the glow around this entire nebula. So the top 4 stars, increasing by right ascension, would be A, B, C, and D. It is a part of a larger cluster of stars. The central cluster is known as the Orion Nebula cluster. About 2,000 of the members are going to be brown dwarfs, what we call these runaway low mass stars, and a lot of accretion disks. So let's look at the mighty trapezium. Every one of these is going to be a multiple star system. We've got binaries and binaries within binaries, so we get quadruple star systems. Only with infrared interferometry can we separate them out. So we can look at the orbital period. We can look at the strength of the winds, or 1,000 times that of the sun. The binary, the primary binary, which is theta 1 Orion C. This is the giant of all of the stars in the trapezium. It is primarily responsible for breaking up the Orion Nebula because it is the bulk of the ultraviolet radiation. It is the bulk of these intense winds. And the magnetic field around here is around 1,100 kilogauss. So you're talking about 275 times the magnetic field strength. So we're talking very intense magnetic fields. Now, there is what we call a fossil magnetic field, where basically, instead of a star's magnetic field flipping back and forth, the magnetic field is still confined to a north pole and a south pole. It doesn't flip back and forth like you would with the sun. So when the magnetic field is fixed in its orientation, it's called a fossil field. The absolute magnitude, if it was within 10 parsecs of Earth, its brightness would be minus 4.9. So it would be brighter than Venus. The surface temperature is 39,000 Kelvin. The luminosity is 204,000 suns. You wouldn't want to be 93 million miles from this star. And it's 2.5 million years old, so it's not going to be a long-living star. There is Theta Orionis A. It's known as the double-double in trapezium because there is A itself, and each one of these is actually a binary. So this is a spectral binary. It has a potential T Tauri star. The A1 has a B-class main sequence star of 15 suns. The T Tauri around the A1 is highly elliptical orbit. The A2 has a binary that is slowly gravitating towards the A1 at a distance of 90 AU, so it's slowly spiraling in. And there is a 4 solar mass star, likely a very cool A-class or a B-class star that makes up probably the A2 star. So we look at the mighty trapezium, we look at the light curves. Sorry. The Theta 1 Orionis B is a multiple star system. It's also known as BM Orionis, so it's a nice variable star. It's an eclipsing binary. We see that there's actually a blue giant with a blue main sequence star, possible between 10,000 to 100,000 years old. But this system is unstable. It only lasts for a few million years because these giant stars do not have a long life. This is so we can go back there. You can see the light curve right there. Every 6.47 days, that represents the orbital period of the B1V here, orbiting around actually it's a blue giant around a, well, some people think it's a G-class giant star. Other thinks it's just a B5 blue main sequence star, which would still make it very, very massive. But then what we have here is the light curve for Theta Orionis E. So we have Theta Orionis D, Theta Orionis E. Again, they both have binary companions. Theta Orionis E, it's actually on the new catalog of suspected variable stars. So that would be an interesting target to observe. Possible subgiant classification at 500,000 years old. There's actually 2 3 solar mass pre-main sequence, sort of baby A-class stars orbiting around the big star. And then this is a spectroscopic companion looking at the change in the spectrum, about a 40-day orbit. But the separation is only like less than 20 milliarc seconds, so it'd be challenged to observe in any telescope. Now, there's every indication that there's possibly, because of the dispersion of the stars in here, that they're looking at possibly some type of an intermediate mass black hole. Something between 100 and 150 solar masses. Why is that? Sorry, why is that? Well, within the central quarter parsec, they're finding that a lot of the gas is being moved around outside of what would be taking place among the stars in the trapezium. Based on the movement of the stars and the velocity of the stars, they're thinking that it probably has a radius of about 1.5 trillion kilometers, because the bigger the black hole, the bigger the event horizon. The gas produced by the main star in the trapezium is about 10 to the minus suns per year, so not a lot of material. But the gas consumed by the black hole is much less. It's about 10 billion times less. So they have to look at the illumination And it's equal to about 10,000 suns, so it's about the same amount of X-ray emissions as the Cygnus X1 system, one of the first confirmed black holes. So we have multiple star systems here, and they're breaking up. So this is what we call a trio of stars being flung out of their birth systems. This is interesting to see. This is the Beckler-Neubauer star. It's moving at nearly 100,000 kilometers an hour. This is the star I. It's embedded in the dust. There's an X star. It's moving at high speed, over 200,000 kilometers an hour. So it's 30 times the speeds of most of the stars inside the Orion Nebula. What's happening is that as these stars are moving fast enough, instead of the field of gravity attracting them, they're doing gravitational slingshots. So we have what's likely a game of gravitational billiards, where the stars are literally knocking themselves around at high speeds because of the gravity, producing a lot of slingshot effects. You can just see how this star has just been moving. That's over a period of 17 years. Now, inside here, this is the Klein-Low Nebula. The center part is going back to the Beckler-Neubauer star. What's interesting about this is that this is the top active star-forming region for the whole of the Orion Nebula. There's lots of X-ray sources. It's only been known for the last 60 years. There are high-resolution maps of this that was made by the Stewart and Catalina observatories. The radiation output is the equivalent to 100,000 suns. The surrounding dust is cold, but the gas is the gas is rather cool at 600 Kelvin because you would expect it to be hotter, like thousands of Kelvin in temperature. But we get a lot of activity in the far infrared. So this is looking through this in the mid-infrared. The problem is this is being powered by what we call masers. So the upper left graph actually shows here the effects of water and hydrogen ions producing huge intense beams of microwave radiation that is piercing the nebula and heating it in the infrared. So as the OMC1 is complex right here, it is the brightest object. It's abundant. There's lots of hydrocarbons and lots of planetary systems being made. I mean, look at this. It looks like an explosion in short time. But look at how the radiation is eating away the dust, the trails, forming the planetary systems. And the radiation output is about 10 to the 40 ergs. So every time it's emitting enough energy, it'd be the equivalent of about 10 million years of solar energy output every second. Okay, so the Theta 2 Orionis system, very complex. I don't know if anybody's ever looked at this. All these stars are in the Washington double star catalog. 2 arc minutes of separation. Each of these are very intense stars. Lots of energy. Speckle interferometry finds a lot of these stars tend to have companions. So there's 13 components between the 2 separate star systems here, both between Theta Orionis 1, the Theta 1 Orionis C, and the Theta 2 Orionis system. It's actually 1 arc minute from each member along the ABC line of those stars. So this is actually lots of variability in X-ray emissions. It's actually a triple star system. You have the spectroscopic companion in the green circle. The blue circle is going to be an O-class star. There's a lot of unexplained, it's virtually unknown why there's a lot of rapid changing emissions in the X-rays, but we're finding that the surrounding gas from these stars varies anywhere from 3 million to 100 million Kelvin. And at 100 million Kelvin, you can simply turn lithium into heavier metals. So I'll briefly go through the Stromgren sphere. It's a bubble of photoionizing radiation. So you get lots and lots of solar erosion. The dust can be pulled back here. As we see with the Orion Nebula, it's not a bubble that goes out in all directions. The radiation is pushed outward along with the galactic winds. The dust is pushed back towards the back right here. You've got the stars that are forming out of here. Because a lot of this gas has been formed from previous generations of stars, This is going to dissipate first. This eats out last. And you get, and some of these stars are so hot, they emit a lot of intense X radiation. So you get more like this blister structure where because of the galactic winds, the radiation bulges outwards, the gas is being pushed backwards, and then this dense region condenses, and that becomes another generation of stars, possibly another trapezium that will form behind it. This is an example of when we look at the luminosity dealing with, I teach this with the kids in my physics class, where this is the Lyman series, this is the Balmer series, and this is more with the ultraviolet, as we have over here, versus this is where we have this with the Balmer series in visible light. So it's from the ultraviolet into the visible light.
Those energy levels.
Yeah, those are the energy levels right there. So you get a photon that strikes an electron right here. If it's highly energetic, it will jump all the way up to this orbit right there. When it emits a photon, it's emitting a photon, not exactly. It generally would equal a photon that's equal to the photon coming in ultraviolet. But sometimes, funny thing about photons, a photon goes into an electron and the electron splits up the photon. So you can actually get like multiple visible light photons from the energy of a ultraviolet photon. So the ultraviolet photon gets absorbed by the electron, it splits off into packs of energy, and you get multiple photons of visible light. And the energy coming in does not always equal the energy coming out, because electrons can be pretty selfish in holding on to some energy. Bach globules, photodisassociation. So the highly massive stars, they have a lot of radiation. They're literally eating away at the less dense dust, and the denser material inside is going to collapse inwards and form a pillar for which new stars and new planetary systems will form. Photodisassociation means basically a breakdown of the dust from more complicated molecules to lighter material. That is, you take a lot of complex organics and you break it down into hydrogen, water, carbon monoxide, and individual atoms. Mostly silica, molecular hydrogen, and frozen carbon monoxide, because in this cold environment, there's just not enough energy for 2 oxygen atoms to bind with a carbon atom. So basically, there's just enough energy for 1 oxygen atom to combine with a carbon atom. So you find mostly carbon monoxide versus carbon dioxide. They're very small. They have just a mass of no more than 50 suns. But these are cocoons that are collections of a lot of water, a lot of amino acids, a lot of nucleotide bases, the very structure for DNA. And in here, they're just collapsing into these stars and planetary systems. So we go back to the Orion bar, we can see a lot of the filaments, we can see these propylates right here. You can see how the radiation acts as a front. It breaks down the complex molecules into lighter gas. So we have the ionization front, the radiation coming from the stars. It breaks up the molecules. They're reorganized into other types of molecules, and we get the complex molecular gas. But look what happens when this stuff breaks away. We're left with these propylates. We're left with these cocoons here. The gas is thin enough to see the disks that are forming the planetary systems. You see that there? That's the orbit of Neptune. So we're finding these propylates with, looks like accretion disks of dust and gas on the scale the size of the solar system that are forming within the propylates. And we can look at this, and one thing is that there's actually a paper here from the Society of Astrochemistry. So when you look using the James Webb Space Telescope, there are thousands of wavelengths of infrared radiation which you can distinguish thousands of complex different chemicals. So we have these cyanopolynines like triacetylene, cyanamide, and acetylene sulfide. We got acrylonitrile and ethyl cyanide. This is one of the chemicals for making synthetic rubber, but we think of these as just man-made substances. We find them in the Orion Nebula. Yeah.
5 minutes.
5 minutes, okay. So right here, just a lot of all these propylates that are forming accretion disks within the Stromgren sphere. I'll just briefly go through this, but what's interesting is looking how we can penetrate at different wavelengths of radiation with different chemical elements and look deep within the structure. These are the jets of gas being blown out, because as gas gets close towards the accretion disk, the magnetic fields from all that dust is blowing out the material. So it cleans out the star of the surrounding material so it doesn't gain too much mass. This is actually looking deep within a propylid up close. And the more you penetrate deeper in, the more you realize that the disk itself is protecting the concentration of water ice looking deep within the propylid itself. So the deeper you look into the propylid, the greater the signature you have for the water ice. Brown dwarfs within the Orion Nebula, lots of brown dwarfs. Some of them within the minimum mass for nuclear fusion, but 20 of them have been discovered. Probably hundreds of more that need confirmation. Not only this is a vast nursery of brown dwarfs, but a vast nursery free-floating planets, these jumbos, these Jupiter mass binary planets. Lots of water-rich faint ultra-brown dwarfs that will not have continuous deuterium fusion, but both water and no water for the two types, 1,200 candidates found so far. And of course, the jumbos. These are what we call these giant Jupiter-like bodies. And we're finding them in pairs. So what's interesting is that they're finding binaries of super gas giant planets that are forming without being around any near star. So this is an example where planets can form probably as clusters of planets, maybe even perhaps terrestrial planets or rocky planets out of the nebula without there being orbiting around any near star. And I like to say that a lot of the complex organic chemistry, the basis of DNA, is likely forming around any type of these planetary fragments, maybe like lumps of rock forming out of the nebula, where life could probably begin out here in space, probably in some lumps of asteroids moving through here, collecting the organics, creating probably the first microbes, and then probably seeding planets. So it may be that abiogenesis is probably happening out here rather than happening on a planet itself, because of what we're seeing more about the chemistry of what's happening here. Because if you can form these small jumbo-like planets, many publications have not yet met peer review approval, but if this is confirmed, then how long will it be before we find rocky planets forming in these nebulas without ever forming around a star? And then, I don't know if anyone's familiar with the Atlas, the Messier Atlas book, because there actually are names for a lot of these structures right here. People like to name things a lot. So it's very good to be an amateur astronomer to look around here and say, oh, this is the fish mouth. Here's Orion's bar. Here's the trapezium. Yeah, this is all visible light. So in very good dark skies, you can see a lot of these structures in very dark skies, but also in photography. But stellar-like bodies, we can see down to like 2.5% the mass of the sun, particularly within the Proboscis Major right here. So a lot of these brown dwarfs and sub-brown dwarfs forming those famous bars, and a lot of bow shocks we see right here. That Kelvin-Helmholtz instability with changes in temperature and density of gases. We see that with our clouds here on Earth. We simulate that with fluids. We see the effects on the sun's photosphere, but we're seeing that effects inside the Orion Nebula itself. Changes of temperature and density. And the bow shocks themselves, I ran out of time, but literally the sharper the angle, the difference, the greater the difference in the sonic and supersonic winds, and how they actually create these bow shocks and shape the radiation, how the radiation is shaping the gas around these newborn stars. And then there's the Herbert-Haro objects, which I probably ran out of time for.
That's okay. Take 3 more minutes.
And I don't know if anybody's ever seen a Herbert-Haro object, but basically what happens is you get an accretion disk, the material gets very hot towards the newborn star, the molecules are colliding, they become ionized, you get electric currents that generates magnetic jets, and the jets are shooting out the extra material, and it becomes a bow shock against the less dense gas and winds around there that creates these. And the Herbert-Haro objects are these jets right here, if you ever have a chance to see them in a telescope. But right here, we can actually identify them We know their locations, so we can go and observe them. Here are some of the videos I actually have. You can see them moving over several years. And this is one from the James Webb Space Telescope. Okay. Star formation, fireworks, clumps of hydrogen and helium. Basically, it's just the basic physics here. Electrostatics, gravity, thermal energy, nuclear fusion, angular momentum collapses the disks, and they form planetary systems as the material collapses under its own mass, with the heavier elements being concentrated towards the center. But that's all forming out of the hydrogen and helium that will accumulate the water in the organic material. That speaks for itself. And that is a Hubble image right there. So, okay.
Wow. Can I say, okay, so what I wanted to do,
Yes.
now is take some time for some Q&A. So we've got about 7 minutes or so available for some Q&A. I would like to say one thing though, okay? Whenever James Wooten or Justin give a presentation, we always learn a tremendous amount. I want to thank both of you guys for the level of presentations that you give, how you expand our understanding of some of the more beautiful aspects of the skies and astronomy.
Bill Pizzeri is not convinced that this is a PowerPoint presentation. Like I'm using some sort of special software that I wrote from scratch.
Yeah, but anyway, so thank you so much, Justin, and James, similarly, you know, when you give your presentations, thank you so much. Do you want to take some time now? Who has the first question for Justin?
Yes.
I have a couple of questions.
Yeah.
One of your earlier presentations slides, you had cubic light years. What's a cubic light year?
1 light year by 1 light year by 1 light year.
Okay, that's a cubic light year.
Or
It's a volume.
9.5 trillion by 9.5 trillion by 9.5 trillion kilometers. So
Kilometers. Okay.
that's just a lot of space in and of itself. The biggest stars would be like grains of sand.
Okay. I saw water in your distribution of all the different elements.
Yes.
There was water.
Mhm.
So how much water is estimated to be in Orion?
Water represents a smidgen of the nebula, but probably enough to form thousands of planets with water comparable to the amount we see with Europa. And Europa has more water than the Earth.
Okay, thank you.
Who has the next question?
No
Questions?
questions? No one brave enough to ask a question?
Okay, Matt does.
Yeah.
Here you go.
So for the jumbo Jupiters,
Yes.
I know for Jupiter, with the moon, I think Io, where the gravity creates tectonic forces, which creates heat and volcanoes.
Yeah.
Could that support life, kind of how bacteria in the ocean are kind of feeding off the energy?
With Io?
No, but from these jumbo planets where if there's a moon that really close that creates friction that could create heat that could create energy for life.
Well, the
Would that
real
be,
question is
plausible?
whether or not these jumbos, if they form by themselves, are actually going to form moons around them. What helps is you have an accretion disk of dust that literally impedes a lot of the ultraviolet radiation from penetrating deep inside, which may affect the ability for a lot of the moons that tend to be mostly of rock and water from forming around it. If these jumbos are exposed by themselves, it's likely the radiation will eat away a lot of the dusty material. So all you have are these super Jupiter planets that may be devoid of any moons.
So you need to have something that blocks the
That
radiation.
accretion disk had dust around it. As we penetrate deeper into it with longer wavelengths of infrared, we see more and more water, which means a lot more ice. And if you see the moons of Uranus and Neptune and Saturn, and most of the moons of Jupiter, with the exception of Io, yes, they'll have orbs of rock around them. They'll be orbs of rock, but they have a lot of water ice.
And that could kind of like Europa, that could be plausible for life.
It's possible, but not if they're exposed by themselves. Because then all what's left of what little matter is concentrated to create a big super Jovian gas giant with these jumbos. And if the jumbos are in binary pairs, then the gravitational tug of war can literally knock around any material from forming into moons. Well, they'll just simply absorb the material. It's like if you have a planet orbiting on a binary, you want to orbit around the two stars, not any one of the stars, otherwise the orbit's unstable.
Okay, any other questions here from the live audience? Of course, the audience online is not dead. Okay, I meant from the physical audience. Do we have any questions from the folks who are online? All right, okay.
Okay.
Justin, again, thank you very much. We'll take a 10-minute break now.
You're welcome.